Welcome to the UAA seminar, College of Engineering seminar series. My name is Dr. Scott Hamill. I'm the professor of civil engineering here. And for today's topic, for those of you new to this, we typically run this seminar every Friday throughout the semester. This semester, we don't have everything lined up yet, but more will pop up. And so today's seminar is run by Dr. Leroy Halsey from the University of Alaska Fairbanks, our neighbor to the north. Given the topic, I would make a note that we encourage this. We are a public university, and we encourage thoughtful research and exploration of academic topics. But obviously UAA and the College of Engineering does not endorse everything that happens here. So, but with that, I will turn it over to Dr. Halsey to give us a thoughtful presentation.
Thank you. Thank you all for being here today. I'm excited about this project that I was fortunate enough to be asked to do. And so before we get started on that, I just point out that they approached me. I turned them down. They approached me. I turned them down. They approached me. And I said, okay, I've lived my life long enough. So I decided to accept it. And that was, I think, in 2014 or 2015, something like that. So I'd like for you all to just take a moment and roam around the room. And so starting up here, let's have everybody introduce themselves so we get to know each other. And that's the way I teach normally in a classroom. And I walk all over the place, but I'm not going to do that today. I might walk in front of here. So anyways, you want to start?
Sure. My name is Rob Jordan. Right now I'm working as a plan review engineer over the community. And I got interested sometime, I don't know, within 5 years after 9/11, and following up on what might have taken place, because it didn't add up to me as to what took place. And then I only learned Dr. Halsey a few years ago when he was taking on the job of trying to reanalyze Building 7. So I graduated from UAF in 1980.
My name's Judy Jordan, and I'm interested because just because of the global effect that this event has had for almost everybody. So I enjoy listening and hearing people ask the questions that need to be asked. So thank you.
Thank you so much.
Hi, my name is Mark Lewinsky. I'm a structural engineer, work for E&D engineers in town. So I've kind of more recently been interested in this, like in the last couple of years, kind of done more research into some of the buildings of Bell, and just kind of curious, and definitely wanted to broaden my understanding of it and get more professional.
Alexander Kharlov, E&D engineers, coastal engineers. For coastal engineer, I'm one of the ignored people. Wouldn't be interested in this, right?
Okay, is that it? So we have a student back there in the back who's in computer science at UAA, I think, right?
Yes.
So anyway, and Scott, thanks for introducing me. I want to kind of start with just kind of giving you a snapshot. This research was requested by the private sector, and they were not. It's basically it's a system. It's a bunch of engineers and architects, 2,600, I think, on the coal right now, and they wanted to get this figured, wanted to get the truth out, and they were pretty sure that there was issues with respect to the report that was authored by NIST, National Institute of Standards and Technology. And if anything, it's an important thing to have as structural engineers, to have the truth, because it affects our what we do. It affects our shall we say, what am I trying to think of? Geesh. Our codes and everything else. And so if the codes are inaccurate, then that's not a good thing for American people. That's not a good thing for the engineers in practice. We have a requirement, really, that we do everything that is correct scientifically, and we don't have any problems. And it's really, really important that we have the truth this is all based on. So this was why they came out and tried to get some help. And we were I was contacted by a John, that was actually in Anchorage. He's a mechanical engineer, but he was a member of that organization, and he actually does medical stuff at the hospital. And that's what he does for a living. Anyway, so I took it on, and the first thing I decided is, okay, I need to get some students to work with me for the research, and I had prepared the proposal so that was in the proposal to pay for the students, and I had in mind getting graduate students, and I made that offer, and I had a whole list of students that were really, really excited about it until they talked to their wives, and they all turned it down. So you'll notice that I have two students up there that were students at the time, but they're no longer students. One of them is a professor in China, came from China, and the other was with South Carolina Department of Transportation, also came from China. So, and they both are in China right now. And Zilli Kwan, the last one, calls me about once a week. I can't call him, but he can call me. It's quite interesting. So, anyway, so this is a structural reevaluation of the collapse of the World Trade Center Building 7. I don't know if that means anything to you, but there was a World Trade Center, the two towers. We saw that on TV. If you were watching TV that morning, breathtaking issue. Turned around, Building 7 was on the east side, about 100 yards away. And you'll see the picture here in a moment. And that building wasn't struck by planes. Yet they said was collapsed by fire. Was the cause of the failure. Now, that's where all the controversy begins, and through that process. Okay, so with that being said, I'm going to kind of take you through the story, and if there's, I won't stop, but I would like to offer the opportunity for you to ask questions. Even Scott, even after this is over with, can they ask me questions? Okay.
Yeah,
So I want to give, and you can call me, or you can even email me. I don't care. What I want to do is make sure you're comfortable and we have communication as professionals to be able to address anything that you're concerned about. Okay, so here we go.
and I should have mentioned too, we are streaming this online, so there's 75 or so. Other
Yeah, and I was aware of that.
Just so everyone else in
So-
the audience is aware.
So anyway, so I want to acknowledge the University of Alaska Fairbanks. They made it possible, College of Engineering and Mines, Department of Civil and Environmental Engineering, and the Institute of Northern Engineering, which is basically Institute of Northern Engineering is where we do all our research. And the College for assisting my graduate students and the directors, faculty, and staff, and so forth. I want to thank the funder, who was Architects and Engineers for 9/11 Truth. That is the group that I was talking about. It's what do you call it? It's not a company for money making. It's what's the name for that?
501c nonprofit.
Yeah, it's a nonprofit. Yeah. And so John Thal is the guy I was telling you about that lives here in Anchorage that contacted me. All right. And independent external reviewers will review the report during the forthcoming public comment period. I can already tell you that occurred in 2020. Okay. And we kept it open for months and had a lot of input from a lot of different people. Wasn't just engineers and architects. It was anybody that wanted to give me comments. We reviewed it, and we responded to it, okay? So anyway, was it peer reviewed? It was peer reviewed by 3 different engineering groups just to make sure that we were okay, all right? WTC 7, or you can call it Building 7, collapsed at 5:20 p.m. the same day that the Twin Towers came down. 5:20 in the afternoon. That's pretty significant, actually, because they were saying the fires were going all that period of time. It's a focus of my presentation today to number 1, present our findings and conclusions for a 4-year study of that building right there. Not the Twin Towers, not anything else going on there, but just this one. We will share our methodology and science that led to those results. And WTC7 is a 47-story building that suffered a total collapse on September 11th. Now that sentence is pretty significant because it took me a year to establish that it was a global collapse and not a progressive collapse. That's significant. That means that there's an area of about 8 stories of all of the columns coming down instantly at the same time, for them within 2 seconds of each other. So that was pretty significant. And I tried everything to prove that was wrong. Wasn't going to happen. So unlike the Twin Towers, that building was not struck by a plane. And so why did it fail on that day? Well, that's interesting. Now, when I took this on, I told the funder, I will not tell you necessarily what brought it down, but I will tell you what didn't. And so that's where I went. And that's what my report is about. Okay. So anyway, coming back, here is a real picture of that area on that day. Okay. And so if I go a little bit more, and that was still, now you're going to see actually what's happening in Lower Manhattan on that particular day. There's your building right in between, and you're going to start seeing a penthouse and everything else come right on down. So look at that. When you see that, and you're going to have an opportunity to see several different views of that, you notice that it's almost straight down. That building was not rectangular. It was a trapezoid. So in looking on plan view of that building, it was a trapezoidal building. So we're now looking in different views of this so you can kind of get a handle on, okay, is that really what happened? So I'm kind of sharing with you documents that were made that particular morning, and that particular day, okay? Which 5:20 in the afternoon, basically. It'll almost make you sick of it. So I'm done, I think. So what I'm going to do is go to the next one. Okay, so now I'm going to kind of share with you what I needed to think about. The items needed for this study was number 1, I needed a structural geometry. Number 2, the floor usage at the time of failure. Now let's talk about a couple pieces in between right after that. Keep in mind that that building collapsed. WTC, the Twin Towers collapsed, and they carried all of the information that a typical person like myself would normally need to explain what happened was gone. They sent it overseas. All the metal, everything. We had people from Fairbanks that went there to help them clean up. That in itself caused people to have health problems because of the dust and everything else they were breathing. So the structural properties I need to have, I'm not going to get it from those pieces because they're gone. They went overseas. Mechanical and thermal properties for the concrete and steel. So I'll share with you how I started getting that information so that I could have a reliable piece of work that we could count on. I needed to determine the thermal conductivity of the structural steel framing, the reinforcing bars, and the concrete. Why? Because the frame was steel, but the floor was concrete. So the floors being concrete were on stay-in-place forms. There's metal again. And the concrete had reinforcing bars in it. So if you really stop and look at thermal properties of concrete, it's a function of the aggregate and whatever else is in it, and the cement and the water And that is different than steel. Matter of fact, it is highly functional to the aggregate. That's about 75% aggregate. So with that being said, you need to know the aggregate. So anyway, I'll tell you a little bit later how I did all that, but I went to that area and I said, what's the dominant aggregate? Because I couldn't find, I was not allowed to communicate to find who had the contract to provide the concrete. I didn't have the opportunity to communicate with the contractors or the building suppliers. I did talk to a person in Fairbanks who used to be one of the subcontractors on that job. So that was pretty informative. But anyway, so where I'm at right now, I needed to determine the thermal strain coefficients for the steel versus the concrete. And I needed to determine the planar centroid of the floor system. So the two things that I did absolutely first, because I was the keynote speaker on the 15th anniversary. And I had already by that time determined that what NIST did was wrong. And it didn't take me but a few weeks to do that, because I focused in on the planar centroid of the floor system and a point of zero movement in the plane of that floor. Now, what does that mean? It means that if you heat up a floor, there's going to be a point that doesn't move. Stuff is going to move around it. And so I needed to find that. And that establishes the direction of movement in every direction. So you can imagine if I had something and I locked it and it couldn't move, then everything, and you heat it up, heat that thing up, it's all going to move with respect to that. All right. And so that, and I had previously done a PhD on this issue, quite frankly, but it was for bridges. So, and it turns out there's so many problems out there with thermal movements on bridges, because it used to have, well, I'm not going to go into all that, but anyway, there's things there as well. Okay, so the UAF modeling methodology is, here's erection and fabrication drawings were used to develop a virtual structure. I had to use what I could. The courts to this day still has everything locked up, so I can't get access to a lot of the stuff that's needed. But I feel comfortable what we did, because we had the erection drawings, we had the fabrication drawings. Programs AutoCAD, I know you all know about that. SAP 2000, Abacus, and SolidWorks were used. And so we started with AutoCAD, and we put the entire building three-dimensionally for all 47 stories into AutoCAD. And then I wanted to use AutoCAD as a mechanism to then take and create the models. So I would take them out of there piece by piece as we were looking at various components of that in a structural model. Dr. Xiao and Dr. Quan used different programs to solve a problem. That wasn't arbitrary. I insisted, first of all, that we had quality control. So every day they were doing work. I would have them come back the next morning, share with what they found. Many times I had them doing the same job. I wanted to see if these two different programs and two different modelers were going to give me the same results. It was developing confidence in my scientific results. That was absolutely essential. So I checked the results every day, and we then would have a discussion about them and once somebody had something slightly different, what did you do to create that? So we examined every one of those little pieces of details. Dr. Xiao performed analyzing using AutoCAD and Abacus. Dr. Quan used AutoCAD, SAP 2000, Abacus, and SolidWorks. Now, I need to clarify a little bit. Dr. Xiao finished before this project was finished. And he went back to, he actually went to, what was it? I think it was Mississippi. That didn't last very long. Then he went to another job, and then he decided that's enough of this. And he headed to, come on in. He headed to China. All right, so Dr. Quan, though, stayed and finished his PhD work. And his work is not only working on this, but his thesis was on fire, on temperature control and fire, and the fire tests that we conduct on building pieces. And there's a requirement that they have to be certified fire tests. 1 hour fire test, 2 hour fire test, 3 hour fire test. Those are coming from certified labs. And so we made sure that we could model those situations and compare to the certified test lab of the papers that were published. And so we did all that before we used what we were doing for this building. Okay, so now my focus was to ensure scientific solutions were not influenced by previous research. Now I'm going to tell you, I did something that you typically, many professors won't do. I said, I don't want you reading about this stuff because it's highly influenced by people that do not know what they're necessarily talking about. They're wanting to paint a picture that may not be correct. We can't afford to allow that kind of stuff influence what we're doing. So I made sure, I ask them every day, have you read anything about this? Please don't tell me you did. So I made sure, I did my best to keep that out of the way. This research was thoroughly evaluated by our peers and evaluated against published literature, okay? And we did everything we could to make that happen. Okay, so the construction of this bridge, and I'm gonna hurry it up here because I'm going all over the place. Construction started in 1983. It was completed in 1987. Height to the roof is 610 feet, 47 floors, 2 million square foot per floor area. That's a lot. 32 elevators. Emery Roth and Sons was the architect, and structural engineering was Erwin Cantor. So the World Trade Center complex is, if you can, I don't have a pointer, but if you take a look at the north arrow is up and to your left, and WTC 7 is up there at the top of the picture, and the two World Trade Center 1 and 2 is down here where those things are sticking out in that blue, if you can see that, okay? So those twin towers are sitting in there. Are you with me? Mm-hmm. Okay, now, with that being said, okay, WTC 7 is located northeast of the Twin Towers. This is important, got to keep it in mind. Northeast, the World Trade Center complex elevation view is what we're looking at prior to September 11th. This is prior to all the damage, okay? So that was prior to that. Here's a little bit different thing I wanted to kind of share with you. WTC 7 different elevation views. I'm showing you floor 13, 16, 19, 22, and 24, and also 5 and 7. Why am I doing that? Well, number one is a lot of the work by NIST was on floor 12 and 13. That's where the fire, they're saying that everything kind of began. Floors in the floor area 5 to 7 to 8 was where a lot of the fire started. Shipping, I'm not saying it didn't have fire in it. I'm just saying it didn't create structural failure. Point of zero movement is really significant. This is a point of zero movement in plan view, okay? And that was very near the elevators. Why would that be the case? Because the elevator system was very stiff. NIST argued the exterior of the building was extremely stiff. Not true. So here's some added information. WTC 7 floor usage on 9/11. I have every floor indicating there what was going on those floors. So you see, floor 13 was Provident Financial Management, 11 through 13 Securities and Exchange Commission. I find it difficult to believe that there was, even if there was fires there, and we know there were some fires, it's hard to imagine that there was plenty of fire combustibles available. Those are financial companies. They're going to lock up everything that you can burn, except maybe the draperies and the furniture and all that kind of stuff. But otherwise, anyway, so that's something that has bothered me for a long time. And we didn't do a lot on fire stuff. We did examine what we thought would be a conservative answer about the fire in this building. But I'm now getting ready to. Well, I'm praying that we can talk to the fire fighters that were in New York at the time this occurred, And the firefighter reached out to me recently and said, hey, can we do this? And so we're gonna, we don't have that stuff in this report, but I'm gonna probably put together a book and have, give them the opportunity to share with them, share with the American people what happened that day. And so it's really quite informative. So anyway, this is the layout of the building. Oh, are we okay? Are you following me in here? Giving you kind of a snapshot of what was happening?
What was the lateral system?
Huh?
What was the lateral system?
The lateral system?
Yeah.
I'll show you here in a moment. There's a system here that, I think I can show that to you in a minute. If not, I'll come back and answer it. Okay. So this is the UAF steel response temperature curve that we have. And so you can begin to see there's a reduction in its ability to carry. This is a reduction factor versus room temperature of what would happen versus yield strength and Young's modulus. Okay. So you can see as you begin to get hotter and hotter and hotter, you're losing the ability to resist strain wise as well as strength wise. Okay. So column 79 is the key for discussion about this, and I'll show you soon where that's at. But here's what that column 79 capacity would have, and the temperatures, there's no argument about that temperature. That's the temperature about where that was at. And so the column itself is not being discussed about its ability to carry load. What is being discussed is the girder that framed into it, the floor, the bearing support, it slipped off of it. That's the argument. And I'll go through that here in just a minute. Are we doing okay?
I got a question. How are you so certain of the temperature? You said you're pretty sure it's.
What's that now?
You said you're pretty certain of the temperature of that column.
Well, because NIST even didn't argue about that. The temperature of the column is not arguable. Everybody pretty much agrees. So they're not saying that caused it.
Well, how would you determine that then? Like, where does that come from?
Well, you need to know where you need to know the fire, you need to know the time that you're measuring it, and you need to know the fire enclosure. Okay.
Mhm.
And we didn't have any of that. So what we did have is a record of everything that they said they had.
Mhm.
That's verbal, you know, and so we used that as a measure, and I made sure that was conservative. In other words, I wanted to make sure that the temperature I was dealing with was the highest it could possibly be for those conditions. Okay, are you with me?
No, I'm following. Yeah, I was just curious.
So UAF material. Okay, material properties that we used were steel ASTM 36 and ASTM 572. Those are the two properties that was in that building. Thermal conductivity for the steel was 35 BTUs per hour per square foot. Thermal strain, density 490 pounds a cubic foot. Modulus was 29,000. That's what we used. Okay. The concrete 28-day compressive strength of 145 pounds per cubic foot. Modulus was around 3,500,000 psi. Dolomite aggregate is what I did is I went around the area and tried to get all the suppliers of the aggregate they use for concrete, and this seemed to be the dominant one, and that's about the best I could do to be sure that we were in the range. And then from Dolomite aggregate, I wrote a paper a few years ago, and I know how to calculate the thermal conductivity, knowing the mix and knowing about how much else and the kind of aggregate. So that's where I got those values. Okay. And that was a peer reviewed paper that I based that on. First, we recommended response. We examined the response to the fire loads. We determined the planar mechanical centroid for the floors 12 and 13. We determined the point of zero thermal planar thermal movement for the floors 12 and 13. And then second, we ruled out scenarios that could not cause a collapse. Then third, we identified types of failures and locations that could have contributed to the observed collapse. Okay, so I want to see, have we given it all the considerations that we could? All right, so methodology. for 3 approaches. One, we simulated the local structural response to fire loading for floors 13 and below. That's where the fires were. So we simulated that by putting those, the student I told you that did all the theory and testing and evaluating against tested fire tests. He and I did this testing, evaluation for these floors, and we know that it's conservative. Any type, we weren't sure there was any fire there, we put it there. In other words, we wanted to know the worst condition possible for those conditions. We examined collapse initiation hypothesis developed by NIST and the collapse hypothesis advanced by private engineering firms that they hired or they were involved somehow, whose studies were commissioned as part of the litigation that was related to the collapse of WTC-7. We then simulated numerous failure scenarios with the overall structural framing system. And for each, we identified the response and what would lead to that total collapse observed on that 9/11. So are we doing okay? Am I moving too fast? Okay, all right. Decisional findings. Number 1, fire did not cause the collapse of that building. So they about had a cardiac when I went there on the 15th anniversary and said it did not. I also said something else. I said temperature was not high enough to cause weakening of the steel framing. It comes back to your question. Further, thermal expansion did not result in a loss of support of the beams and girders, yet NIST claimed that was the case. And I'll explain to you why they said that here shortly. And WTC-7 did not experience a progressive collapse as claimed by NIST and others. It was actually a global collapse. Now, I tried for a year to prove what they said is okay, and I couldn't. It was not possible. It didn't happen that way. Okay? Let's take a look at this building. To your right is a video record of the actual collapse on that day, that afternoon. The firefighters, by the way, I'm going to share with you something. The firefighters tell me that they were in that building. That and the fire marshal came in and said, "This building's going to collapse this afternoon. Get out of it." There was somebody there that was actually measuring the amount of movements that were going on. That confuses me, and I don't know who that was. So I want to find out if that was actually a firefighter, if that was actually an engineer. I understand that they had an engineer in there. I would like to know who that was. I'd like to communicate with that person. But somehow they said, no, go down to the restaurant there on the corner and we'll wait for the building to collapse. And so all of them went there. And that's what happened that day, based on the last conversation I've had with firefighters. And I keep in mind, I didn't have any firefighter information at all. Trying to get information to do this, of course, wouldn't let us see anything. Anyway, so this is
What caused the fire?
huh?
Where did the fires come?
From the debris that was coming off of the Twin Towers. Okay, and it actually hit in the southeast corner of the not southeast corner, southwest corner of that building, somewhere around 5th or 6th floor. And we did look at if that could have caused the problem of a failure, because some people thought it did. Okay, so the UAF collapse simulation, I'm going to simulate, you notice I have it on still. Okay, so here's what's going to okay, so the history. The National Institute of Standards and Technology, NIST, reported that WTC-7 collapsed due to fire at 5:20 p.m. on September 11, 2001. And NIST also reported no other tall steel frame building had ever failed due to fire. And I don't have a disagreement about that at all. That's true. To this day, it's still true, assuming that we're right. Okay, so it's essential for enduring public safety that the failure mechanism for this structure be understood. And that's what we're all about here. Therefore, architects and engineers for 9/11 Truth funded that to this university, UAF, to re-examine that WTCF collapse. The key findings by our team was, number one, approach. One, NIST overestimated the exterior wall rigidity. Subsequently, NIST argued that floor expansion was westward as it moved from the east exterior wall. Now, are you following what I'm saying? This is significant. Do you understand that the exterior wall, imagine, is on your right? Okay, because that's east side. Okay, west side is on your left. So what they're saying is that that exterior wall on the east side was so stiff that it would not allow any movement. So everything moved. When you heated up the floor system, it's going to move westward. That's what they said. No, not true. That exterior wall was not stiff. What was stiff? The most stiff was at the elevator shafts. So actually, exterior walls were flexible and the thermal movements were from the point of zero movement near the elevators. Therefore, planar thermal movements were from west to east, pushing the exterior wall outward and not the other way around. Okay? Are you following me here? NIST argued that girder A2001 moved off of the bearing seat at column 79. UAF found that the movement at this seat was in the opposite direction and was very small and not an issue. The UAF findings also showed that relative movement at A20 to the base plate on column 79 was 3.68 inches for non-composite, 2.18 inches for partially composite, and less than 1 inch for composite behavior. Now, are you following what I'm saying? The concrete slab has shear connectors that are fastened to the girders and beams. And if it's full composite, it moves as a system, except there is some movement thermally, interactively, that's causing other stress. Because the concrete is going to move at a different amount of strain than is the steel because of thermal properties. Okay, so that's what was going on. Okay.
Question.
What's that?
Why would it move more for non-composite?
For what?
If I'm reading this right, it says that it's moving 3.68 inches for non-composite, but only 1 inch for composite.
That was steel only, no concrete slab, nothing. It just,
Oh,
the thermal expansion of the steel is higher than the concrete, so it moves. Okay. Now, so that's for non-composite. Throw in partially composite. I'm saying, oh, there's slip resistance at the interface between these two. If there are now shear connectors, there's still going to be resistance.
saying that the concrete is restraining steel.
Yeah. Okay. And we did that with 2 different programs to just see how much it was interactively. Okay. Then NIST. Okay. So,
Is this Abacus?
huh?
Did you do this in Abacus?
I did it with Abacus, I did it with SolidWorks, and I did it with SAP. I got pretty much the same answer on all 3 programs.
And earlier you said that the thermal conductivity, the effective thermal conductivity was about 1.4 for 1.3 for concrete.
No. If I said that, erase it.
It's on a slide.
Yeah. So the concrete thermal strain is a function of the aggregate, and it can be as much as almost identical to the steel, or it could be all the way to 12 times 10 to the minus 6 degrees per degrees Fahrenheit, so forth. Or it can be 2. It depends on the aggregate. It depends on the concrete. You see what I'm saying? So I used dolomite because it's the most probable aggregate that was used in that, but I don't have the proof of that.
Right.
Okay.
But then there was a bullet point that said with the rebar, there was an effective thermal conductivity.
The rebar does affect it. for sure, and we did look at that.
So my question is.
Yeah.
Was that effective thermal conductivity applied isotropically, or because you're gonna have different thermal conductivity in the planar direction than you're gonna have in the Pickett's direction?
We did account for that, and we did include the rebar, and the rebar has a thermal conductivity that's the same as that steel.
Right.
And so that increased that of the composite concrete by itself. We did account for that. Okay, not only that, but there was another factor. There was a structural forms, and the structural forms had basically a what do you call it? It was basically a U-shaped in one direction, stiff in the other direction. I counted for that too, because it was stiffer in one direction than the other, and it thermally moved in those two different directions. And so, are you with me? All right. So, okay, I've talked about this. So, okay, so here's column 79 we've been talking about. Notice that is the north arrow is over here, that direction. This is the northeast corner of those interior columns. Here's that exterior wall I was referring to. That's flexible. Overall composite movement of column 79, SAP 2000, gave me 1.92 inches to the right, 0.73 inches vertically, if we heated up the floor, okay? And notice I said composite, okay? 1.85 and 0.94 for Abacus, really quite close. As far as I'm concerned, that was close enough, all right? So the movement to girder A2001 relative to column 79,413 is really the argument. This is where NIST and us really highly disagree. Floor slab to steel framing condition, NIST and UAF. I just made a correspondence. If you take a look at composite, UAF says the composite movement of that system is less than 1 inch. But NIST didn't do that. Otherwise, there would not be a blank there. Partially composite, 2.18 inches to the left. Non-composite, they took all the concrete away. They said there were no shear connectors, and therefore this is not, so they didn't account for it. They said 5.5 inches of movement to the west. 3.68 inches to movement is what we calculate. NIST later revised their girder movement to 6.25 inches after being alerted that the bearing seat was actually 12 inches wide and not 11. So this is after they'd already submitted a report and they came back and said, no. NIST only examined for the non-composite condition. So Scott, that's what they did, okay? Are you with me? All right. So key findings of UAF research team continued. Abacus, a finite element program, we used it to model the solid elements. And you guys, do you still have Abacus here? We don't at UAF anymore. So anyway, thank God you guys got it. These elements were used to evaluate, huh?
I have to pay for it.
Well, I know that. Yeah,
The
And my
the
program-
University doesn't pay for
I know.
it, so.
And that's a shame. But we had, our research was paying for it when we used it, you know. Anyway, and it's a great program, by the way. It's really, really good. So, find out, we used it for the floor framing. These elements were used to evaluate the validity of NIST collapse initiation hypothesis. And the NIST assumptions were the following. Okay, number one, the exterior east wall was fixed. That's not valid, it was flexible. Are you with me on this? We're talking about the east wall, right-hand part of your body. Shear connectors on several beams were broken. We saw no evidence to consider this to be a valid assumption. NIST assumed no shear studs were on girder A2001. There were shear studs. All the drawings showed that they were there. NIST assumed bolt fastening girder A2001 to the seats at columns 44 and 79 were broken. That was also an invalid assumption. So using NIST assumptions, and if girder A2001 were heated, it would get trapped behind the west side plates of the flanges on column 79. I'll show that in a minute. Just bear with me. I'm just preparing you mentally to see the argument. We considered movement to the west to be invalid because the east exterior wall was considered fixed, and that was not a valid assumption. Further, column flange side plates would have prevented the girder from walking off its seat, and that didn't happen either. So let me show you what I'm talking about. And then I'm going to talk about that in a minute. Approach 3, we used SAP to three-dimensionally simulate numerous failure hypotheses. In each case, we examined failure modes and evaluated if they would lead to the total collapse observed on September 11th. Based on our analysis, we found the following. Number 1, column 79, 80, and 81 did not fail at the lower floors of the building as asserted by NIST. That had everything to do with that bearing seat, because all those columns were nested together, basically, by beams. If column 79, 80, and 81 could lead to failure of the next row of core columns, exterior columns at the southeast would be overloaded and the building would tip. That would have been what would have happened if you followed that logic. Simultaneous failure of all core columns, but not exterior columns, would cause the building to tip to the southwest. Okay. Simultaneous failure of all core columns over 8 stories, followed at 1.3 seconds later by the simultaneous failure of all exterior columns over 8 stories, produced almost exactly the behavior observed in the videos of this collapse, which you saw earlier today. That's what I determined, and that's basically a global collapse. I generated that term global collapse because it became obvious after 11.5 months that we were not going to find a progressive collapse at all. We looked at so many different options, and there was some engineer said, you've got to look at that. You got to look at it. Well, I was looking at it. There was just no way to show it was going to happen. Based upon situations or simulations, the collapse of WTC7 was a global failure involving near simultaneous failure of all columns in the building, and not a progressive, which I've mentioned to you before. Okay. Details behind the science. In the following slides, I will attempt to go through the details of our study. How we dig on time?
Yeah, about 10 minutes.
Huh?
About 10 minutes, 12 minutes.
Okay. All right. So, structural expansive movement. First, we determined we determined planar mechanical and thermal centroids by floor 12 and 13. Then we developed nonlinear spring stiffnesses of the connection. And what I haven't told you yet is we went through every connection on floors 12 and 13 and simulated them by putting springs that would replace what that was. And then we subjected it to a load displacement to get the stiffness. And we have nonlinear stiffnesses. In other words, not linear. So we took it all the way to failure to simulate the breaking of the bolts and the movement of the connection type that we were dealing with. So second, we developed a nonlinear spring stiffness for the connection, beam to girder and girder to column. Then we developed an equivalent nonlinear spring for the computer model. Third, the concrete floor was using stand-place steel forms, which means stiffness of the floor was different in mutually perpendicular directions. So that was accounted for by developing elements that accounted for that geometry change. And so we have the stiffness of the floor system accounted for in the 2 different directions. Fourth, we examined planar thermal lumens for the floor composite behavior, all shear studs in place, partially composite, frictional resistant between the concrete and the steel beams, and a non-composite in which we allowed no shear studs or frictional resistance, which is where they were at. Okay. Here's 413. There's your column 79. Up in the upper left-hand corner are displacements that we were getting out of the computer models, and the color will tell you basically like 6.844 inches right in here. Column 79 right in here. See that green? That's about, what was it? About Okay, so the worst there is 1.63 inches. No, that's not true. Yeah, it is. 1.63 inches, okay? And in that case, all right, that's floor 13. Floor 12, almost identical. So those two floors. Now, column 79 at floor 13, 1.5 inches in the east direction, 1.94 in the other. So this is looking at it slightly different, but that's the spot where that column is at. And why am I looking only at that? Because that's what the argument. That's where NIST said everything started. And so if I can't get it to pop off of that support system, it's not going to do that. So evaluation of NIST hypothesis. Here's the column 79. There's the, if we can have a big picture here to a right and take an examination, we could all have a better understanding of what's going on. So this A2001 is from 79 out to 44. Kind of gives you an idea, okay? And those other columns, 79, 76, 80, and 81, kind of gives you the column system on floors 12 and 13, all right? NIST argues that the absence of girder shear studs caused the girder not to have sufficient lateral restraint, and the failure of the girder to column connections were caused primarily by thermal expansion of large span lengths of the northeast floor beams. Okay, they weren't arguing about the columns failing, they were arguing about the expansion in the floor failing. So NIST, absence of girder shear studs, it said all the movements going this way, because this is stiff. Not true. And so this is where, over here in this red area, is where they're marking up the tree. So the NIST argues that this is the horizontal thermal deformation. You got to remember that that's not the case in my analysis. My analysis is way over to the left is where the middle of this building by the elevator shafts, which is really stiff, and movement went from there to the east, not to the west. Okay, so here's that column. I mean, here's that W33 by 130, and it's girder A2001. Okay. Court records state that the 30 shear connectors were equally spaced along that girder. So they were there, but they ignored them. Okay. NIST conclusions were: first, fire-induced weakening of critical columns, but did not cause them to collapse. Temperature in column 79 was below 200 degrees C. Horizontal beam movements were caused by thermal expansion, and lateral displacement of the girder framing into column 79 was a result of thermal expansion of the beams framing into that girder. Okay, so that's kind of a snapshot of what they said. You lost all vertical lateral restraint between floor 8 and floor 13 because of all that movement. Cause loss of lateral support over 9 floors caused it to buckle and lose. But if it doesn't drop off of that support, that's not going to happen. Okay, so here's column 79. Okay, area of floor connections were modeled from floors 8 to 14, and we looked at it very carefully. All right, outside the selected area, connection failures were not modeled by NIST. NIST used fixed or pinned. Now, this is another significant thing that I'm bothered by. Connections were not modeled by NIST for any exterior wall. So let's get back to that for a second, and I'll show you a picture of it. To the right, half of the building, they simulated connections, kind of like I did, but not nearly as good. To the left of it, they used pin and fixed to simulate two different behaviors. Yet that's what they did. I think they ran out of time or effort or got tired or whatever. So girder was considered to have lost vertical support when its web was no longer supported by the bearing seat. That's important. Bearing seat at column 79 was 11 inches wide. That's when the girder at column 79 had been pushed laterally at least 5.5 inches. It was no longer supported by the bearing. That's their stuff. Okay. Remember that they came back and said, wait a minute, it's 6.25 inches of movement. When they found out that they needed to have that. Okay, NIST results. This is the actual footage of the building. This is their simulation. Okay, now keep in mind that somewhere up there to the right of the penthouse, right near the middle of the building, in the plan view of the floors, they didn't have springs to represent the connections in half of that floor. The other half they did. Okay. So in the NIST study, no connections were modeled along the outside of the frame. So this is basically, look at the penthouse going on, and here's their model. I don't think it looks exactly like the real building. Okay,
Is that looking from the north?
huh?
Is that looking from the north?
I missed that. What did you say?
Or is the angle from the north?
It's basically from the south, I think.
Towards the north,
Yeah,
looking towards it.
yeah, we're looking south. We're looking from south from north. I
From
think.
northwest.
Yeah, northwest.
In the video.
Oh. This is what they have. Oh, you're right, Scott. This is the north direction. Here's this side over here. Outside selected area connection were not modeled. In other words, pinned and fixed. Over there in the blue, they used connections that they modeled. Okay. So again, this is their penthouse at the top. You're going to see, this is a still drawing. I'm going to show you here in a minute what this is going to do. And you can see there's different stiffnesses vertically in this system. Down in this area here is where, on the southwest side, is where the system was penetrated by the debris from the towers, and they were on fire. So UAF now of the NIST collapse initiation hypothesis and propagation claims, a solid final model of structural members in the northeast corner of 413 of the 413 was generated. Final was also performed to replicate results in the NIST report at girder A2001, which was pushed off or rocked off its seats by column 44 and 79 to initiate the collapse. That was their stuff. Here's the column 79. You'll see girder 2001 up there, girder 2015, and another girder A2002. Another thing I want to point out to you, up there 44 to 42, they did not see the bracing between that exterior girder that's going across from left to right, 44 to 42, outside, top of it. There's members between it to the next girder. See that? They didn't use them. They threw them away. Yet it buckled out there. So, anyway, take all that and put it down into what it really looks like. Here's what I'm referring to, G3005, and there's braces in there to keep that thing from twisting and buckling and all that kind of stuff, okay? So floral framing a computer model for 413. This is another view of that, just kind of giving you a snapshot. UAF Abacus computer model, column 79 was built up, was a built up of column with side plates. It's really important that you understand this. This is a W14 by 730 standard structural shape that was used for column 79. They then put these plates, 2 by 26 inch built up side plates. Okay. That's what was there. That's what it looks like looking down on top of that column. Here are the side plates. Here is the seat for that column, for that girder, A2001. And when it heated up, it tried to, which way was it moving, by the way? It was moving from what? East to what? West? Because why? The exterior framing was stiff, so they pushed it to our left, as you're looking at that. Okay? Now, that's what that looks like. That's what it looks like in our finite element model. With the assumed temperature distribution from NIST, I'm using their temperature now, and original loading condition, the side plate on the flanges of column 7 would prevent girder A20 from moving to west more than 3.5 inches. Couldn't do it. It's not possible. Thereby preventing A20 from losing its support at the bearing seat. So you got to take that off the table. It's not going to happen. This is taking a look down and looking up of that area. This is the exterior column beams, or exterior columns at W24 by 55 floor beams. And then column 44 and 79. I'm not going to spend any time here. It's not so important that you understand a lot of that. So, but what I am referring to is that area up there I already called your attention to. See where they took away those bracing members. The diagram demonstrates that two beams close to 79, E3004 and K30 have buckled in the analysis, not mine, because we know that they were there.
What were those braces?
Huh?
What were the braces?
I don't remember at this moment, but they were sufficient enough to prevent it from laterally having potential loss of lateral restraint. Okay. So, and you can see here that they also have buckling here. So the diagram demonstrates that two beams close to column 79 buckled, and also they're down there near at the top they also did. Okay. And then more evaluation of NIST analysis. The next 5 slides show in the simulation floor 13, even if the side plate was not part of column 79, girder A200 would still not have been failed due to loss of beam support. Why? Because my direction is different than theirs. Okay. So this is looking down on top. This is looking at the end of that girder and how it's going to be supported into that beam seat, bearing seat. All right. This is kind of another picture of it. This is where I'm actually showing you the beam seat, and we also were simulated. See that picture to the left? We simulated all those connections. We put them in by physical geometry, and then subjected it to a load, more than one load, and obtained the displacements. And then from there, we were able to get stiffness, linear stiffness, and then we increased the load, and we created a nonlinear curve. Okay, to get for shear as well as for axial as well as for bending. Okay. What we're looking at here on the end view is stiffeners that we didn't talk about that was also in there that they didn't include. So those stiffeners are significant, and you'll see it in my picture over there. It was actually in the building. Those stiffeners were there. So there is your girder. How it's coming in. Some more pictures of the thing, concrete slab, metal deck. There's a system of how it would have shoved without the stiffener plates, without the plates that are sticking out there to resist it. Another picture of it. Okay, the NIST approach. 5.5 inches of movement at the girder bearing support in column 7. Issues that led to that 5.5 inch movement was non-composite main girders, neglected thermal expansion of the concrete slab, separated connection modeling from the pin and fixed connections, and mixed web flange stiffeners. Okay. this kind of gives you a snapshot of comparison of what we did versus that. I'll just let you take a quick look at things that I made a connection, I made a comparison to see why our answers are so different. Okay. Okay, I'm gonna go, is that okay? We all right? All right. And as far as, we subjected, we did a study on the fires and we decided to use their fires because they were more conservative, they were worse. And if we couldn't create a failure, we knew that we were okay, right? So we used the same fires they did. Huh?
Wrap it up.
Okay, I'm in the process, nearly there. Thank you. WTC7 abacus modeling, you can begin to see how I did it. This is an abacus model, and those are little finite elements, breaking it up into tiny little pieces for the floor, for the walls, for the columns, for everything. Okay. This is a comparison connection between the deck and the beam. UAF sample connection response. There's basically, I'm just going to run through these quickly because that's what we did. We modeled each one of them and looked at their behavior. Okay, you can begin to see how we were doing it. We actually took the shape, broke it out into pieces, and started examining it. We got moment rotation curves, shear connection curves, all that. SAP 2000, we compared SAP and abacus all the way. So what about the actual collapse? We evaluated possible failure modes using SAP 2000. I'm going to skip right through failure at the substation level. So this building was setting on the substation. To this day, I don't know. We didn't have enough information to evaluate if the substation had failed. Couldn't do it. We tried everything we could find to do it. So I could only do so much around that idea. Okay. Anyway, radiant heat from the towers and one influence of the building and so forth. Okay. That's what we did. I'm trying to get there, Scott. I'll be there in a minute. This is our failure. This is a UAF collapse simulation. Velocity is red, and the actual building collapse velocity by David Chandler was in green. He's a physicist, and he plotted it on that building. So what about the collapse? We evaluated the progressive collapse hypothesis, but we found it did not do that. So global collapse simulation perspective one is basically we've seen. Try to get out of here in a couple of minutes. First global collapse simulation in perspective two. The simulation was done to compare with the collapse footage, and the collapse initiation was set at 4:13. Okay.
Here we're going to show you a videotape of the collapse itself.
Describe that.
Now we go to videotape the collapse of this building.
Now I'm going to say one thing here. You saw a picture of the penthouse going down and only went so far. Everything that we see, the penthouse failure, support failure, was up around floor 45, the 45th floor, not at the bottom, not in floor 13, not in floor 12 where the fires were. There was no fire up there. So this was a different this is a different failure that was occurring. So anyway. Second global collapse simulation perspective one. The simulation was done to compare with the collapse footage set at floor 19. Not exactly sure where this all started, but we're looking at different floors where it might have started. So not a whole lot of second global collapse. Okay, same kind of thing.
Here we're going to show you a videotape of the collapse itself.
Describe that.
Now we go to videotape the collapse of this building.
Okay. So we then looked at progressive collapse, simulation for NIST assumption. And the simulation was based on NIST assumption in column 79, buckled and floor 13, Progressive collapse was simulated with the help of static analysis. And it got pretty, it's pretty significant to say we couldn't get it to come straight down. Again, the tilt. That was case 2. We looked at several. So this is like, again, some more of this stuff. And we begin to take out the columns as it would begin to fail and take it from one step to the next to the next. So these, the green circles signify the static axial load didn't exceed the load capacity of those columns. But there's columns out of there now that was in there previously in the previous slide. And so as we go through, we begin to see as the thing begins to develop that other columns were lost and they're counting on more. There's different 3 green ones now. And so we begin to look at all of that, deformations within the floors of 12 and 13. Now you see that the failure of these columns will be enough to start a progression of column failures. This is progressive collapse. And you begin to see that more columns fail and so forth. I'm taking you to a really fast visualization of this. And no columns available to carry load at the end of the result, and so forth. So basically what's happening is that building is running into all kinds of things that would have happened if it was progressive. WTT7 then did not fail due to fire. It did not experience progressive collapse. It came down as a global failure in free fall. That penthouse failed in column 7. It lost support at or near floor 45, way up there outside the fire. Above the fire, this failure occurred approximately 5.5 seconds before all the inner core columns failed. After the inner core failed, 1.3 seconds later, all exterior columns at the same floor failed. There was about 8 stories, by the way. While the failure could have occurred over 8 floors at various heights, the building video footage showing floor 17 to floor 47 moving downward as a result, as the unit suggested, the failure occurred at or below floor 16, most likely. Okay, don't know that for sure. Any questions? I'm done. So, Scott, I have a couple of minutes, I'm sorry. Are we okay? Hope I didn't bore you.
Right on. All right, well, thank you for coming.
Yeah, yes.
I'll ask a question, litigation wise, is there any advantage for anybody of your evaluation versus the other one? This is whatever it is, I'm not an engineer, but is there any advantage for, because there's a lot of litigation going on because of that?
You know, I wish life was simpler. We as an engineering community need to know when we design something that code is correct. Right now, we can't say that.
And that becomes the courts and they won't give information, all this stuff.
And they won't, I mean, there's been 2 lawsuits, I think, filed against NIST, and they just ignore it. There's no way to get them to respond that I'm aware of. And I'm not part of that whole game. I just did the research. But I would be happy if they would be willing to do it, is to say, listen, let's have a debate. I would be willing to do that. But I bet you they wouldn't. You know, I don't know, I hope they would, but I've offered that idea lately to say, okay, let's have a debate. Let's roll up our sleeves. Let's go after it.
And the other day I saw a program on how concrete is made, and the elements going into it is the most important part, because cement, how that's produced determines your stability of your concrete. And did you ever, it looks like you didn't get any answers on those, that part of it either. So there's so many questions still open.
There are, but so what I tried to do is to make sure that I was within the realm of range. And so I kept it within that box. So even if I didn't know it completely, the probability of it being outside of where I was at was taken care of. That's all I could do, I don't know. I mean, I've examined a lot of failures over the years, and we usually have information. You know what I mean? We did have the structural drawings, we did have the erection drawings, we did have all that stuff. That was significant. But didn't have some of the other stuff we really needed. I want to thank you all for coming. I hope I gave you some insight that might be helpful, so.
Thank you.
Yeah. you bet.
Thanks. Business for those people that are online, if you're looking for the PDH code, it is STEEL, STEEL. So that is the code that you need to put in to get your PDH credits for the engineers. So that's it. Thank you, Dr. Halsey.
You're welcome, Sam. Hey, Scott, could I get a copy of everybody that attended, including them? You know,